Thank you so much, dear colleagues. Please allow me to say a few words about the radiochemical purity of gallium peptides without any human scans or without any animal scans, just pure radiochemistry. And I want to say sorry in advance if I'm going to talk about some well-known things. But again, the gallium is the most used radionuclide radio metal for the PET, and principally as peptidic vectors for the transmembrane tumor receptors. These radiopharmaceuticals based on different bifunctional chelating agents like DOTA-NOTA and peptidic vectors of octreotide derivative or RGD derivatives. So we have some different combinations like DOTA-TOC, DOTA-T, DOTA-NOC, DOTA-blah blah, NADAG, RGD, and other. Some school course of the chemistry. So based on the amphoteric nature of gallium, there are three main radiochemical forms of gallium may be found in radiopharmaceutical preparation. It's a bounded form, it's a colloidal form, and it's a free form of gallium. At last, in the 8th edition of the European Pharmacopoeia, we have the monography for the gallium erythritide or gallium DOTA-TOC, where all these impurities described, and describe the limit for this, and describe the methods just to measure these impurities. So what about the gallium in the colloidal form? Pharmacopoeia recommends for us the thin layer chromatography with ITLC system with ammonium acetate and a mixture of water and ethanol. And in this system, the peptide moves with the solvent front and the gallium colloid stay in the origin. Some people, some scientists think, some scientists claim that free gallium in this system moves with the solvent front, but in fact, free gallium in this system stay the origin the same. So actually, this first peak already contained the gallium in the colloidal form and the gallium in the free form. And if you forgot about it, further calculation will give you underestimated results due to the duplication of the free gallium content in your preparations. Thanks God that today there are many good publications where after clearly indicate that free gallium in this system stay at the origin on the chromatogram. But still, in some papers here you can find these instances that gallium moves in on this system. Maybe the reason it's due to the different reference standards for this. Just for example, if you put the stock solution of the gallium, the generator eluate in this system, we will see the main signal, the origin of the chromatogram. But if we will use the gallium, it's just a little higher concentration of HCl, 0.2, the gallium will move. But of course, in your radiopharmaceutical preparation, it can be happen because it's at the pH range. In this manner, I think other system not so widely used, but still well known. It can be better. This is a system of the mixture of the saline and methanol and the proportion 5:1. In this system again, the peptidic fragment moves with the solvent front, and the gallium colloid and free form of gallium stay at the origin. It's absolutely the same, but in this system, the peak corresponding to the gallium peptides is fairly narrow and symmetrical, and this system is really fast. For example, for the 75 millimeters development of the strip, it takes only 4 minutes versus 20 minutes for the pharmacopoeial method. And the correlation between these two methods is around 1. But again, this system is just a little fox-like in the corresponding to the free gallium, because if you put the stock solution of the gallium generator eluate in this system, you will see the main signal with the retardation factor is around 0.5. But in the pH range or the concentration of the radiopharmaceuticals, the free gallium will stay the origin of the chromatogram. So what I want to say here that the generator eluate is a not very good reference just to determine the position of your free gallium in your radiopharmaceuticals when you try to develop or try to test some chromatographic systems. And of course, for the free gallium pharmacopoeia recommends for us HPLC. It's a very good method. Some scientists use also ITLC method with a citric buffer, where free gallium moves with a solvent front. I really like this method too because it's very fast and very simple and with a high reproducibility. But in our department, we think about the new method just to separate all these three spaces of the gallium, three forms of the gallium, just for the direct measuring of the colloidal free form and labeled form. And it looks like that we found it. And very simple system. It's ITLC SG with a water solution of 3-fluoroacetic acid. So in this system, peptide stay at the center of the chromatogram with retardation factor around 0.5. Colloidal form stay at the origin of the chromatogram, and ionic forms of the gallium move with the solvent front. It looks like very nice with a good resolution, not less than 3 or 4 sigma. And of course, this system is fasten out. Again, for the 75 millimeter strip, it takes 2-3 minutes. RF retardation factor for the gallium, it's invariant to the pH or the HCl concentration. It always moves with the solvent front. And this system now tests for the different compounds. And in our department, it was validated for galli-dotatate, nodagonok, and nodag-RGD, monomer and dimer. The cross-validation work for every specific form showed good correlation between other used methods, and you can see here, this is a citric buffer method. Here is a free gallium amount, 47%. Here it is 47%. Here is a pharmacopoeia method with ammonium acetate and methanol. Here is a peptide. This is model preparation with all free spaces. 40% of the peptide. Here is a 40%. Here we see the real amount of the colloidal form. Just to be sure, we make the electrophoresis. Here is a paper electrophoresis with not a very good resolution because it's paper. But you see the amount is almost the same for the moving peak. And this is the gel electrophoresis with a good resolution. And the correlation of this method with the other is very good. And of course, various synthesis is, in the cases of the normal synthesis for the routine synthesis, there is a good correlation between this method and HPLC method. You see here it's 94%, but with some colloid correlation, it's 98%, and here it's 98% because colloid never can be seen on the HPLC, of course. And the last thing that I want to tell you, it's really maybe scary, maybe strange thing, but in the cross-validation work, we tried to take some different samples with different amount of free gallium of the colloidal form, much higher that it can be seen normally in routine practice. And for example, this one, this was the solution, was tested with our method and other TLC methods, and the radiochemical on purity, of course, 78, it's not purity, it's on purity, with a big amount of the free gallium. But when we tested with the HPLC, it was 98%. First, we think that we're crazy or something gone wrong. We just check the chromatographs, change the columns, but again and again the situation was repeated. It is not necessarily means that you will find this situation in your routine work, but see, just look here, the difference between the TLC methods and the HPLC methods, it depends on from the pH level of your solution. Of course, here in the normal area of the radiopharmaceuticals, there is not so high, and I told you with the normal routinely preparations, there are good correlation between this method and HPLC. But you see, something strange can be seen here, and I think it's important to take it into account, especially when you do some research and development of new drugs, because sometimes in good papers you can see that the labeling efficiency was carried out only with HPLC. So, and thank you for your attention.
Question?
Hi, very nice and very useful presentation. And I have a rather comment than a question. To avoid surprises, you have to validate your HPLC method.
Yep.
And a very important part of that validation is the control of the recovery of the column. So before using any HPLC method, you have to perform those experiments and just show that nothing is getting stuck on your system or on your column. And whatever you get on your chromatogram corresponds to the reality.
Yeah, thank you. Of course, we have validated this method, and normally there is a good recovery. And when we check various activity, it of course was remained on the column, not on the loop, not in the injector. And only in this model preparation cases, we think about some gallium species that can be sorbed in the matrix of the column, because we changed different columns and used different methods and validated methods from Pharmacopea, recommended methods, and everything. But this situation was repeated again, not only in our labs, but in the other labs.
Yeah, but it cannot just disappear. You have to find it somewhere.
Yeah, it always remains in the column. Yeah.
Thank you.
Thank you.
Question over here?
Just a short question. Did you consider the speciation of the gallium in the presence of chloride due to the formation of the gallium chlorocomplexes as a function of pH?
Sorry.
So in the presence of chloride ion, there is a formation of gallium chlorocomplexes.
Yeah, sure.
And is also the speciation of the gallium as a function of the pH in the presence of constant chloride concentration is depend on, the pH, of course, and the hydrolysis of the gallium. And did you consider during your separation the type of speciation?
On the TLC method?
Yes. And also in the HPLC.
All these forms with chlorocomplex or with the gallium tetrahydroxyanion, it's moved with a solid front every time.
Tetrahydroxy is not formed.
Sorry?
In this pH range, tetrahydroxy is not formed.
Tetra
Only the 2-hydroxy and mainly 3-hydroxy species. Tetrahydroxy just pH up to 8.
Yeah, but this form is moved with solid front every time.
Any other questions? No, thank you very much.